Let's talk now about CNN architectures. CNN architectures really started to become important in 2012. So we had an ImageNet challenge. This ImageNet challenge was, again, these 1,000 different labeled images. So what happened was they downloaded a bunch of images from the internet, came up with 1,000 different possible classes, and then got Mechanical Turkers, right? So Amazon Mechanical Turk humans to do this labeling. However, instead of giving each Mechanical Turker an image in a list of 1,000 categories, which would have just been brutal to do, instead they basically gave an image and asked whether it was either just a particular category or not. So they would, give an image and say, is this a bird? Give another image and say, is this a cat? Give another image and say, is this a dog? No, actually not a dog, because part of the 1,000 different categories is actually 120 breeds of dogs for some reason. So here's an image. Is this a Hungarian Vizsla? Is this an image? Is this a Boston Terrier? Things like that. These challenges ran, let's just give some numbers here. So if we look, for instance, at 2010, and we look at, so here we've got the year. This is the top 5 accuracy. Top 5 accuracy basically considers you to be accurate if the actual label was in one of the top 5 of your predicted labels. So you got a picture of some sort of a dog, and you predicted it was a Boston Terrier, and that if the top prediction was a Boston Terrier, second was a Grand Mastiff, third was a Vizsla, fourth was a something else, fifth was a something else. And if it was, in fact, a Grand Mastiff, then you were considered to be accurate. So it's easier than actually being a top 1 accuracy. So if we look at those numbers, in 2010, this would have been, let's say, about 71.8% accurate. And in 2011, more like 74.2%. 2010 and 2011 predated neural networks in this challenge. So it was in 2012 that we had our first neural net, and that was AlexNet. AlexNet was the first real neural net to be using GPUs. So it actually used 2 GPUs and spread its model across the multiple GPUs with some computation that was passed from one GPU to the other GPU. And so they got a really big jump, so from 74.2% to 83%, 83.6%. In 2013, we had AlexNet with some modifications. And these modifications increased the accuracy to 89.3%. In 2014, then, we had 2 competitors come in, VGG and Inception, V1. And Inception jumped up into the 90%, so 92.7%. And VGG got 92.7%, Inception 93.3%. 2015, then we had ResNet. ResNet jump again up to 96.4%. As we look at the accuracies, we see this steady improvement. But keep in mind, for example, the jump from 93.3 to 96.4, you can think of it as sort of 3%, but it's really, in some sense, much more. So if we look at the error rate went from 6.7% down to 3.6%. So if you think of that, that's really almost a 50% improvement, right, in the error rate. And so that's massive. After that, we really don't have this challenge anymore. It's not challenging enough. It turns out that this is better than human performance. Okay, well, it's not better than all human performance. It's not better than taking this wisdom of the crowds by using Mechanical Turk. Instead, if you have any single humans, their error rate is probably worse than 3.6% on this top 5 accuracy. How do we know that? A bored grad student actually sat wrote himself up a little web app that would go ahead and present images, and then he would put what he thought the result was, and his result was that he got something worse than 3.6%. I think somewhere around 5% was about human accuracy. He tried to get some fellow grad students to help. They got too bored too quickly. So that's the CNN architectures. We are going to be talking about VGG, Inception, and ResNet, and look at some of the things that they did that make them work, and what the improvements are, and how these improvements come from VGG to Inception to ResNet. Although the ImageNet challenge is no longer present in this form, it is present in a more complicated form. So the problem has gotten harder, where not only do you need to note what category an object is, but you also need to specify the bounding box of it, so where it is in the picture. And then there's a more complicated challenge where you are presented pictures with multiple objects in them, and you have to not only categorize them, but actually provide the bounding box. So if you've got a picture of someone sitting on a sofa in a living room in front of a TV, and there is a coffee table with a flower on top, the model would need to note the person, the sofa, the table, the flower, and the TV, and also provide the bounding boxes around all of those. So that provides some more challenge.